Hello, class. I'm here to talk about the last problem that I assigned for chapter 10. As I promised, I would do my best to record it. I really want to get some videos for chapter 11. It's been a crazy, crazy, crazy day, like I believe most of you as well. But here I am. I want to go over this problem because we did talk about a mean and two simple means which, by the way, this might have confused a lot of people. I was just trying to separate this formula for you. So this is how I did right here, the top, the sum of the difference, which is minus 14. Right here, the bottom, this formula right here, this simple size times the sum of the difference square. So all I did is this simple size, which was 8, times the sum of my difference square, and then this formula right here, the sum of the difference is square. So the sum of the difference square. So right here is 14 square. And then right here is my simple size 8 minus 1, which is 7. And then you're going to do the square root of all of this. I hope this clarifies a little bit. I want to start on problem 108, which is talking about two independent population proportion. These are the formulas we're going to be using, even though they might look very complicated. Really, for example, on your test statistic, you're going to be always using the z-score. Okay, so right here, all it means is that they're getting the proportion of the first set of data and then subtracting the proportion of the second set of data, which it could be proportion of the proportion. It could be a number 1 here and a number 2 and a number 3, but they use ABC, which on the template I have put ABC as well, so you can follow along with this formula, but it could have been different. In order to calculate this formula, there you're gonna have to be getting what is called the pool proportion formula. The pool proportion is the value of the first x, and then plus the value of the second x, which is going to make sense when you see the problem, divided by the simple size, the first simple size plus the second simple size. And let's go to the problem. The questions I have gotten from Appendix E, and I have put it here. Again, you're not being asked to sketch the graph. I did sketch it before, and I put over here. You might notice very minor difference on the digits because it really depends if you're referring to a cell with several digits or you're just typing the value. But it basically, these are the values you should be getting for this problem. And let's go and get started so you'll make more sense. Right here it says two computer users were discussing tablet computers. And it says a higher proportion of people aged 16 to 29 use tablets than the proportion of people aged 30 and older. This is very poorly written, but it's just basically saying that people of the age between 16 and 29 use more tablets than people age 30 and older. Okay, so a higher proportion. Well, right here, you have got your parameters. You know it's a proportion problem, correct? You're noticing two different set of data. And here it says higher, not higher and equals. Go here to your little cheat sheet. You're gonna say which one is a higher proportion. Well, the only one here is higher is this one over here is my alternative hypothesis. Well, therefore we have to use this right here. We choose uh, this for our null hypothesis and alternative hypothesis. Therefore, for your null hypothesis. Well, if your, let's start with the alternative. If your alternative hypothesis, it's gonna be PA. I'm just, instead of putting P1, I'm just trying to keep it consistent with this formula right here. It says that PA is higher than PB. Why did I start on the alternative hypothesis? Because there is no equality sign, and the only ones that do not have an equality sign, it's right here on the alternatives. So I start with that. Therefore, if this is higher, my no will be the proportion of A. Did I say probability before? Not sure. And then less or equal than the probability of B. And that's what we're trying to prove. Okay. Let's go ahead and calculate this so we can have the numbers that we're going to be plugging in when we get to the test statistic. Again, this is always saying is the proportion of the first set of data minus the proportion of the second set of data, right? Divided by the square root of the, they call the pool proportion or the weight average of the proportion times 1 minus the pool proportion again times 1 divided by the sample size of the first set of data and then plus the second um, set or the second sample size of the second set of data. Did that make sense? You let's put in the formulas and hopefully that will make more sense. In order to calculate your proportion, let's look at these two numbers first. We're gonna do equals to 69 divided by 628. And the second one, we're gonna do 231 divided by 2,309. And for your proportion A, you have about 11%. Your proportion B, you have about 10%. Let's go ahead and calculate your pool proportion, which is really gonna be the sum of these two values, which you could call as the x values. So the sum of 69 plus 231 divided by the sample size, the sample sizes. 628 plus 2309. And then you should get about this value. If you want to go ahead and add a digit, that's fine. That's what I said. It really, when you calculating, if you type the value or if you just refer to the cell, it might give you very a minor difference. In words, um, clear state what is your random variable. We know we are working with proportion, correct? And it's telling you right here on alternative that a higher proportion of people aged to 16-29, or we have a higher proportion. So we can just say that my variable is going to be that proportion 1 is higher than proportion 2, which is a higher proportion of people aged 16 to 29 use tablets. Then the proportion, I'm going to move the formula of people age 30 and older. Okay, that's what we're testing here. I'm going to put it down here because we're going to be using very soon. Let me lower a little bit. What is the distribution? I said we're going to be using a normal distribution for two independent population proportion. Okay, and well, one thing that you know here, if you do remember the little trick that if you have your alternative hypothesis with a greater sign, which is pointing to your right, therefore you have a right tail test, which means you only gonna need this. You only gonna need this value right here. This portion, this shaded area right here from your table, not a two tail, not a left tail. You're just going to need this portion right here. So what is my test statistic? That's the part that I said is this formula right here. If you want, we can do separate. We can do the top, and I'm going to type the numbers instead of referring to the cell so you can see the numbers, and it might give you a very little difference from this. If not, then I did something wrong. So 99, well, as long as I type the number right. And then for my bottom portion, I'm gonna do the square root of, and in Excel you put one parenthesis in the wrong place and it's all gone. My pool proportion right here, which is 0.1021 times, actually this portion here is times this, correct? So let's see if that's gonna work the way I expect. If not, then I'm gonna just have to do it again. Minus my pool proportion again. I'm just following this pool proportion times 1 minus my pool proportion times 1 divided by my sample size A, um, plus 1 divided by my sample size B. And I really want to know until I do this value, which is the top portion divided by the bottom portion. And I just hope it's right. And that's exactly what I was expecting. So let me put a few more digits. Yeah, I really had a value a little different because, like I said, I refer to the cells. See 0.721, 0.727. I could go ahead here and modify so you will see that it will change a little. And then for the second one right here, we're gonna have this. See, you already modify. And if I change the bottom, then it'll go ahead and it'll modify as well. But I'm just gonna leave it right there because it actually matches over here. I just want to show you how you adjust it to what I have on my graph. Okay, so what is my p-value? Well, you can you could use an Excel formula, which I'm gonna show you, but if you're not comfortable with it, I rather since it's a Z table, it's more simple. I just gonna go refer to the table. I'm sorry, I find it more simple. The T table can get a little trickier. Okay, so right here we're looking, let me make it bigger. We are looking for the value 0.721. 0.7, okay, not 1.7. So here start with point. So if you take the 0.7 and then let's go to 0 and then 1 and then 2 right here. So the value would be a little higher than this, around 0.7643 or so. Okay, but let's use this percentage right here for our p-value. So based on this test statistic for the z-score, we have a 0.7642, correct? And then you look over here and you say it's wrong. Well, actually it's not wrong because we are only asking for this side of the table. If you go over here to your table, you're gonna notice that it's giving you all these values, but this little portion. So what we need to do, we need to do 1 minus the value that I just found, which is about 0.236, which in here 0.2354. I don't know if it won't help much, but there we go. I told you it would be a minimum difference. Okay, I have not put exactly for 0.721. I have put for 0.72. Okay, if you want to check another way, since we are using a normal distribution for two samples, you could go ahead if you're comfortable with formulas and then start typing norm for normal distribution right here. Use S for the sample distribution. We're working with samples, correct? So your Z you have defined as this, right? And let's put true for um, cumulative distribution function. Okay, so again, so there is your z-score, and then here explains cumulative distribution function. If you want to look at that, do you see how it got just a little higher because it's 0.721? So if I would deduct, I still need to deduct because it calculated for me this side of the table. Point, there we go, 235. 0.235. There we go, 0.2354. That's how that value got there. But if you don't want to do the formula, that's fine. If you're not comfortable with it, then just go and look at the Z table. Then to conclude, is asking you, oh, sorry, I forgot to read the rest. Test at the 1% level of significance. Okay, so your alpha is 1%. So if your alpha is 1%, and your, which this is the value, and your p-value is 2354, well, the alpha is less than or equals to, so let me put the symbol here, your p-value. Therefore, what do you do if your alpha is less or equal? You do not reject the null hypothesis. And then the reason for your decision, the p, or you can either say that alpha is less than p-value, than the p-value, or you can say the other way around, p-value is greater than the alpha. Conclusion, well, we had a 1%, correct? At the 1% level of significance, there is not, there is no sufficient evidence to conclude um, that a higher proportion of tablet owners are age, I don't like, I could just keep going, but are age 16 to 29 years old, then are 30 years old and older. And that would be the end of problem 108, chapter 10. Problem 80, again, you're probably not going to be seeing it. It got a little tricky on the whole calculation for your test statistic. Problem 108, you might see a proportion, two independent proportion in your final exam. Actually, you might see for the mean, but this, I would say that if you're gonna be going over the homework for your final exam, definitely take a look at 42 and 44, problem 108. Excuse me, the ones that I have presented for chapter 9 as well. And right now, let me take a look at chapter 11 and see how many videos I can get in so you can work on your homework. And I really hope this helps a little. Thank you.